Right now, at this exact moment, somewhere in the Milky Way, an intelligent civilization may be looking up at their sky. They might be standing on the surface of a distant world, under an unfamiliar set of stars, watching points of light scattered across their night, wondering what lies beyond them. They may have built cities. They may have developed technologies we cannot imagine. They may even believe they are on the verge of reaching the stars. And just like us, they might be asking a question that has echoed across every thinking species that has ever existed. Are we alone? It is a simple question, but hidden inside it is an assumption so deeply embedded in our thinking that we almost never stop to examine it. The assumption that if other civilizations exist, they could eventually reach us. That given enough time, enough intelligence, enough technological progress, the distance between stars is just another challenge waiting to be solved. But here is the uncomfortable truth. It doesn't matter. Even if the galaxy is filled with millions or even billions of intelligent civilizations, none of them are coming here. Not because they lack curiosity, not because they lack intelligence, not because they lack the desire to explore, but because the universe itself has made it almost impossible. This is not a story about whether alien life exists. This is a story about why the laws of physics make it extraordinarily unlikely that any of them will ever reach Earth. Because the barrier is not technology. The barrier is not engineering. The barrier is reality itself. A reality shaped by three forces that every civilization must obey: distance, energy, and time. Together, they form something invisible but absolute, a kind of cosmic prison, not built by intention, not designed by any intelligence, but emerging naturally from the structure of the universe itself. And once you begin to understand how these forces work, you start to see the universe differently. Not as a vast ocean waiting to be explored, but as a collection of isolated islands, each one separated by distances so extreme that they might as well be unreachable. To understand this, we have to begin with something deceptively simple, something you have already seen countless times: the night sky. Go outside on a clear night, look up. You will see stars scattered across the darkness, some of them faint, some of them bright, some of them clustered so closely together that they appear almost connected. Your eyes interpret them as nearby. Your brain processes them as neighbors. It feels intuitive, natural, almost obvious. But it is wrong, completely wrong, because the night sky is lying to you, not intentionally, but fundamentally. What you are seeing is not a map. It is a projection, a flattening of something so vast that your mind has no way to process it correctly. Two stars that appear side by side in the sky might be separated by dozens, hundreds, or even thousands of light years. They may not belong to the same region of the galaxy. They may not even exist in the same era. One could be relatively close, a dim red dwarf quietly burning just a few light years away. The other could be a massive blue supergiant, shining from hundreds of light years in the distance, its light having left long before human civilization even began. But your brain compresses all of that depth into a flat dome of light, because that is what it evolved to do. Human perception was never designed to understand the scale of the cosmos. It was designed to survive on the surface of a planet, to judge distances measured in meters, to track motion across fields and forests, to estimate the reach of a thrown object or the speed of an approaching threat. Nothing in our evolutionary history prepared us to intuitively grasp distances measured in trillions of miles. So when we look at the stars, our brain simplifies, it flattens, it reduces the incomprehensible into something manageable. And that simplification creates one of the most persistent illusions in all of human thought. The illusion that the stars are close, that they are destinations we could, one day, simply travel to, like cities across a distant ocean, like islands waiting to be discovered. But interstellar space is not an ocean, and the stars are not islands you can sail between. They are separated by distances so vast that even our largest comparisons begin to break apart. Consider the Pacific Ocean. At its widest point, it stretches roughly 11,000 miles across. On a human scale, that is enormous. It took centuries of technological advancement to cross it reliably, and for much of human history, it represented an almost insurmountable barrier. But now compare that to the distance between stars. The nearest star system to Earth, Alpha Centauri, is about 4.24 light-years away. That number sounds small. 4.24. You can say it in a second. But a light-year is not a human unit. It is not a distance you can visualize. A single light-year is the distance that light travels in 1 year, moving at nearly 300,000 kilometers per second. That is about 5.88 trillion miles. Multiply that by 4.24, and the nearest star is roughly 25 trillion miles away. 25 trillion. It is a number so large that it stops behaving like a number. It becomes an abstraction. If you tried to count to 25 trillion at one number per second, without stopping, without sleeping, without taking a break, it would take you nearly 800,000 years to finish. You would begin counting before the rise of ancient civilizations, before the pyramids, before written language, and you would still be counting today. And that distance, that almost incomprehensible gap, is the shortest possible journey to another star. Not the average, not the farthest, the closest. Now imagine trying to cross it, not in your imagination, but in reality, with a machine, a physical object, something that must obey the laws of motion, the limits of energy, the constraints of time. Humanity has already launched the fastest objects it has ever built into space. One of them, Voyager 1, has been traveling outward from Earth since 1977. It is moving at roughly 38,000 miles per hour. At that speed, it can circle the Earth in less than an hour. It has traveled farther than any human-made object in history. And after more than 4 decades of continuous motion, it has covered about 15 billion miles. That sounds impressive, until you compare it to interstellar distances. 15 billion miles is less than 1 light day. Not a light year, a light day. The nearest star is over 4 light-years away. At its current speed, Voyager 1 would take approximately 73,000 years to reach Alpha Centauri. 73,000 years to reach the nearest star. That is not a journey. That is a timescale longer than the entirety of recorded human history, multiplied several times over. And when it arrives, it will not stop. It cannot. It has no mechanism to slow down. It will simply pass through and continue into the darkness. A silent object drifting through interstellar space, carrying a message that will likely never be received. This is the reality of interstellar distance, not the version we see in movies, not the version where ships jump between stars in minutes, but the real version. The version where even our fastest machines barely make a dent in the distance to the nearest neighbor. And this is where the illusion truly begins to collapse. Because once you understand the scale of these distances, you begin to see that the problem is not just difficulty. It is not just engineering. It is not something that becomes easier with better technology. It is something deeper, something built into the structure of the universe itself. Distance, at this scale, is not just space between 2 points. It is a barrier, a fundamental separation between worlds, a separation so vast that even imagining crossing it requires us to abandon every intuitive sense of distance we have ever relied on. And yet, distance is only the beginning, because even if a civilization could somehow accept these distances, even if they were willing to attempt the journey, they would encounter something even more unforgiving, a second barrier, one that does not just measure how far you must travel, but how much it will cost to move at all. Energy. And beyond that, something even more relentless, something that cannot be stored, cannot be reversed, and cannot be escaped. Time. Distance opens the door to the problem, but energy and time are what make the door impossible to pass through. And once you see all three together, you begin to understand something profound. The universe is not just vast. It is structured in a way that keeps everything apart. Even if intelligent civilizations are everywhere, they may never meet. Because the stars are not just far away. They are separated by the laws of reality itself. To understand why distance becomes an absolute barrier, we need to stop thinking in human terms. Because every instinct you have about distance is wrong at cosmic scale. Let's start again with the nearest possible destination, Alpha Centauri. It is often described as our closest neighboring star system, 4.24 light-years away. That number sounds manageable. It sounds like something you could, in principle, travel. But the moment you translate that distance into something real, it begins to break your intuition apart. 1 light-year is about 5.88 trillion miles. So Alpha Centauri sits roughly 25 trillion miles from Earth. 25 trillion miles. Try to picture that, not as a number, but as distance. If you could travel at the speed of a commercial airplane, around 900 kilometers per hour, it would take you over 3 million years to get there. 3 million years. That is longer than Homo sapiens has even existed as a species. And that is just the closest star. Now move slightly farther out. Sirius, the brightest star in our night sky, is about 8.6 light-years away. Twice as far. Vega, one of the most well-known stars in astronomy, sits about 25 light-years away. Now the distances are no longer measured in trillions of miles, but in hundreds of trillions. And yet, these stars are still considered part of our local neighborhood. They are nearby, in galactic terms. Now expand your view further. The Milky Way galaxy contains an estimated 100 to 400 billion stars. Our solar system is located about 26,000 light-years from the galactic center, orbiting within a small structure known as the Orion Arm. We are not at the center. We are not at the edge. We are somewhere in between, in a quiet, relatively unremarkable region of the galaxy. From here, the nearest stars are a few light-years away, but the far side of the galaxy is about 100,000 light-years distant. That means if you could somehow travel at the speed of light, the fastest possible speed in the universe, it would still take 100,000 years to cross the Milky Way. Not a spacecraft, light. The absolute cosmic speed limit. Even light cannot make that journey quickly. Now pause and consider what that really means. Light travels at approximately 300,000 kilometers per second. It can circle the Earth more than 7 times in a single second. It reaches the Moon in just over 1 second. It reaches the Sun in about 8 minutes. And yet, to cross our galaxy, it needs 100,000 years. This is not just large, this is beyond scale. It is a level of vastness that removes any meaningful sense of connection between regions of space. Now go beyond our galaxy. The nearest major galaxy, Andromeda, is about 2.5 million light-years away. That means the light we see from Andromeda tonight left that galaxy 2.5 million years ago, long before modern humans existed. What you are seeing is the past, and between us and Andromeda, there is nothing. No bridge, no pathway, just millions of light-years of empty space. And Andromeda is close. In cosmic terms, it is right next door. Beyond it, there are trillions of galaxies, spread across an observable universe that spans about 93 billion light-years. 93 billion. Again, a number that stops behaving like a number. It becomes something abstract, something impossible to visualize. Because the human brain was never meant to grasp distances like this. And this is where the real problem begins. Because when people imagine alien civilizations visiting Earth, they rarely think about where those civilizations would actually be. They imagine something nearby, something close enough to reach. But the galaxy does not work that way. Stars are not evenly packed. They are separated by vast regions of emptiness. On average, stars in our region of the Milky Way are about 4 to 5 light-years apart. That might not sound like much, until you remember what a light-year actually represents. Even in the densest parts of the galaxy, stars are still separated by distances that make travel between them extraordinarily difficult. Now consider probability. Let's assume that intelligent civilizations are rare. Perhaps one emerges for every 10 million habitable planets. That might still result in thousands of civilizations across the galaxy. But the galaxy is enormous. Those civilizations would be scattered across 100,000 light-years of space. The nearest one might be thousands of light-years away. Not 4, not 40, thousands. Now assume the opposite. Assume intelligent life is relatively common. Perhaps one civilization for every 100,000 habitable planets. Even then, the nearest civilization might still be hundreds of light-years away. Because the galaxy is not just large, it is sparse. It is mostly empty. And that emptiness matters, because it means that even if the galaxy is filled with life, Each civilization is separated by distances so extreme that they might as well be alone. To make this more intuitive, shrink the Milky Way down. Imagine scaling the entire galaxy to the size of the continental United States. At this scale, each star becomes a tiny grain of dust, barely visible. Our Sun is one of those grains. Alpha Centauri, the nearest star, would be another grain, just a few centimeters away. That seems close, reachable. But now look beyond that. The next nearest stars would be meters away, dozens of meters, hundreds of meters. Civilizations located 1,000 light-years away would be in entirely different regions of the map, across states, across vast distances of empty land, and the full width of the galaxy would stretch from coast to coast. Most of that map would be empty. This is what the Milky Way actually looks like. Not a dense cluster of stars, but a vast expanse of nothing, with isolated points of light scattered throughout it. And this is the key insight. Space is not just big, it is empty, profoundly empty. Between stars, there is almost nothing. The interstellar medium, the material that fills the space between star systems, has a density of about 1 atom per cubic centimeter. For comparison, the air you are breathing right now contains around 25 quintillion molecules per cubic centimeter. That means interstellar space is billions of times more empty than the air around you. It is a vacuum so perfect that it is difficult to even describe. Cold, dark, featureless, no landmarks, no reference points, no natural pathways. A spacecraft traveling between stars would not be moving through a medium like water or air. It would be moving through almost complete nothingness, for years, for decades, for centuries, with no sense of progress, no visual confirmation of approach, just distant stars that barely change position. And this creates a psychological illusion, because from inside a star system, everything feels close. The planets are nearby. The sun dominates the sky. Movement feels meaningful. But the moment you leave that system, you enter a scale where movement becomes almost meaningless. You can travel for years and still be almost exactly where you started in relation to your destination. And this is why distance is not just a challenge. It is a barrier, a fundamental separation between worlds, because every mile must be crossed. Every kilometer must be traveled. There are no shortcuts, no hidden pathways, no natural corridors that make the journey easier, just empty space, stretching across unimaginable distances. And this emptiness introduces another problem: navigation. When traveling across interstellar distances, precision becomes everything. Even the smallest error can result in total failure. If a spacecraft deviates by even a tiny fraction of a degree at launch, that error compounds over time. Across light years, it becomes enormous. A deviation of just 1/10,000th of a degree could cause a spacecraft to miss its target star system by millions or even billions of miles. Not slightly off course, completely lost. And correcting that error requires energy, which adds mass, which increases fuel requirements, which feeds back into the same problem again. Every solution creates another constraint, and all of it comes back to distance. Distance defines the scale of the problem. It determines how far you must travel, how precise you must be, how long the journey will take, and how much energy will ultimately be required. But perhaps the most important consequence of distance is something far more subtle: detection. Because before any civilization can travel to another star, it has to know where to go. And finding a planet like Earth from across interstellar distances is extraordinarily difficult. Earth is small, tiny, on cosmic scales. It orbits an ordinary star in an unremarkable region of the galaxy. From even a few light-years away, it is almost impossible to see directly. It does not shine, it reflects, and the amount of light it reflects is minuscule. Even detecting Earth's atmosphere requires incredibly precise measurements, looking for faint signatures of oxygen buried in the overwhelming brightness of the sun. And beyond a certain distance, those signals disappear entirely. Humanity's radio signals have been leaking into space for just over a century. They form a sphere, about 100 light-years in radius, Beyond that, Earth is silent, invisible, undetectable. A civilization 1,000 light-years away has no idea we exist, because our signals haven't reached them yet, and when they finally do, they will be so weak, so diluted, that they may be indistinguishable from background noise. So even if intelligent life is common, even if civilizations are scattered across the galaxy, they are not just far apart, they are hidden from each other, separated not only by distance, but by the limits of detection itself. And this leads to a realization that is both simple and deeply unsettling. Even if someone is out there, they probably don't know we exist, and we don't know they exist. Not because we aren't looking, but because the universe is too large, and the signals are too weak to bridge the gap. Distance does not just separate worlds physically, it separates them informationally. Each civilization exists inside its own bubble of awareness, a bubble defined by the speed of light. And beyond that bubble, there is silence. Not because nothing is there, but because the information hasn't arrived yet, or never will. And this is only the first layer of the problem. Because even if you could somehow overcome distance, even if you could map the stars, identify habitable planets, and choose a destination, you would still face something far more unforgiving. Because crossing that distance requires energy. And the energy required is not just large, it is staggering, far beyond anything any civilization can easily produce. Distance sets the scale, but energy sets the price. And that price may be too high for any civilization in the universe to pay. Distance defines the scale of the problem, but energy is what makes that scale almost impossible to overcome. Because in space, you don't just need to travel far, you need to move fast, extremely fast. At the speeds we use on Earth, interstellar travel is not difficult, it is meaningless. If you move too slowly, the journey does not take decades. It takes tens of thousands or even millions of years. So the only way to make interstellar travel even remotely practical is velocity. You have to go faster, much faster. And this is where physics begins to push back. Because increasing speed is not a linear problem, it is exponential. Every increase in velocity demands disproportionately more energy. And as you approach a significant fraction of the speed of light, that energy requirement begins to explode. Let's start with something simple. Imagine a small spacecraft, not a massive starship, not a floating city, just a robotic probe, about 1,000 kilograms, roughly the mass of a small car. Now ask a simple question. How much energy would it take to accelerate that probe to just 10% of the speed of light? Not half, not near light speed, just 10%. The answer is about 4.5 times 10 to the 17th power joules of energy. That number is difficult to grasp. So let's translate it. A large nuclear power plant produces about 1 gigawatt of power. That is 1 billion joules per second. If you ran that power plant continuously, at full capacity, it would take about 14 years to produce enough energy to accelerate that single probe. 14 years of an entire power plant for one small object. And that is just acceleration, not deceleration, not life support, not communication, just getting up to speed. Now compare that to humanity's total energy output. Every power plant, every engine, every source of electricity on Earth combined produces roughly 6 times 10 to the 20 joules per year. The energy required for that one probe is about 1,000th of all the energy humanity produces in an entire year. For a single mission, for a single object, with no crew, no return trip, no margin for error. And it still takes over 40 years to reach the nearest star. Now let's make this more real. The Hiroshima atomic bomb released about 6 times 10 to the 13th power joules of energy. The kinetic energy of our probe at 10% light speed is equivalent to roughly 7,000 Hiroshima bombs. 7,000, compressed into motion, not an explosion, not destruction, just movement. This is the price of speed, and this is only the beginning. Because everything becomes worse when you try to build a real spacecraft. The moment you add more mass, the energy requirement increases proportionally. Double the mass, double the energy. But in practice, it's even worse than that, because of something known as the rocket equation, a principle that governs every propulsion system that carries its own fuel. The rocket equation creates a brutal feedback loop. To go faster, you need more fuel, but fuel has mass, so adding fuel makes your spacecraft heavier. And a heavier spacecraft requires more fuel to accelerate, which adds more mass, which requires even more fuel. This loop grows exponentially, not gradually, not predictably, exponentially. For chemical rockets, the kind we use today, this becomes catastrophic almost immediately. Reaching even 1% of the speed of light would require a fuel-to-payload ratio so extreme that the spacecraft would need to be almost entirely fuel. Reaching 10% of light speed? Mathematically impossible. The amount of fuel required exceeds the mass of the observable universe, not because we lack better rockets, but because the equation itself does not allow it. So engineers look beyond chemical propulsion. They turn to nuclear, fusion, antimatter, more advanced ideas. But every one of them runs into the same wall. Nuclear propulsion improves efficiency. Fusion promises more energy. Antimatter offers the highest energy density theoretically possible. But none of them change the fundamental relationship. Mass, velocity, energy. That relationship is fixed, and it is unforgiving. Take antimatter, often imagined as the ultimate solution. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy. It is the most efficient energy source in the universe, in theory. To accelerate our 1,000 kilogram probe to 10% light speed, you would need about 500 kilograms of antimatter. That sounds manageable, until you realize how much antimatter humanity has ever produced. Across the entire history of physics, every particle accelerator on Earth combined has produced only about 20 nanograms of antimatter. Not grams, nanograms. A billionth of a gram, 20 of them. That is everything we have ever made. Producing just 1 gram of antimatter would cost tens of trillions of dollars and require enormous amounts of energy. To produce 500 kilograms would require resources that exceed the total output of human civilization for millions of years. And that is for a small probe. Now scale that up, a real spacecraft, something capable of carrying humans, life support, radiation shielding, food, water, redundancy systems. You are no longer dealing with 1,000 kilograms. You are dealing with millions, tens of millions, perhaps more. The energy requirement scales with it. The fuel requirement explodes. The problem becomes so large that it stops being an engineering challenge and becomes a physical impossibility. And then there is relativity. Because as you push toward higher speeds, something strange begins to happen. The universe resists you, not metaphorically, literally. According to special relativity, as an object approaches the speed of light, its effective mass increases, which means each additional increase in speed requires more energy than the last. At 50% of light speed, you need significantly more energy than classical physics predicts. At 90%, the required energy is multiple times higher. At 99%, it becomes extreme. At 99.9%, it becomes absurd. And at 100%, it becomes impossible. Because reaching the speed of light requires infinite energy. Not a very large number, not an impractically large number. Infinity, which means no object with mass can ever reach it. Not us, not aliens, not anything. The speed of light is not a challenge to overcome. It is a limit built into the structure of reality itself. And this creates a trap. Because the only way to reduce travel time is to increase speed. But increasing speed requires exponentially more energy. So you are forced into a trade-off. Go slow, and the journey takes thousands of years. Go fast, and the energy cost becomes impossible. There is no middle ground, no optimal solution, no breakthrough waiting to happen. Every path leads to the same conclusion. The universe charges an enormous price for motion at interstellar scales, and that price does not depend on technology. It does not depend on intelligence. It does not depend on how advanced a civilization becomes, because the minimum energy required is set by physics, not engineering. You can build better engines, you can reduce waste, you can approach efficiency, but you cannot go below the minimum. The universe sets the price, and the price is non-negotiable. Even a civilization capable of harnessing the full energy output of its star would still feel the cost. They could afford it, but it would not be trivial. Launching a single interstellar mission would consume a measurable fraction of their total energy. Launching many would become a massive undertaking, and every mission would still take decades, centuries, or millennia to complete. Energy does not solve distance, it only makes it survivable, barely. And even if a civilization accepts the cost, even if they generate the energy, build the ship, and begin the journey, they are not free. Because the moment they leave their star system, they enter a new problem. One that energy cannot solve. One that no amount of power can overcome. Time. Because even if you can pay the energy cost, you still have to endure the journey. And the journey is longer than any civilization is guaranteed to survive. Distance sets the scale. Energy sets the price. But time is what makes the entire endeavor begin to fall apart. And this is where the problem becomes something deeper than engineering. Because now, it is no longer just about reaching the stars. It is about whether any civilization can survive long enough for the journey to matter at all. Distance defines how far you must go. Energy defines what it costs to get there. But time determines whether the journey means anything at all. Because even if a civilization solves the problem of distance, even if it generates the unimaginable energy required to accelerate a spacecraft to a fraction of the speed of light, there is one thing it cannot escape: the passage of time. Unstoppable, irreversible, indifferent. Let's return to something that sounds, at first, almost reasonable. 10% of the speed of light, 0.1 c. It is often described as a benchmark for serious interstellar travel. At this speed, a spacecraft moves at roughly 67 million miles per hour, fast enough to cross the entire solar system in days, fast enough that distances within a star system begin to feel small. But once you leave that system, the illusion disappears, because even at 10% of light speed, the nearest star, Alpha Centauri, is still over 4 years away. That means the journey takes more than 40 years, one way, not a round trip, just getting there. Imagine boarding a spacecraft at the age of 30 and arriving at your destination at 70. That is the closest possible star, the shortest possible journey, the absolute best case, and nothing can go wrong. Nothing can fail, nothing can break, for over 4 decades. Now double it, because if you want to return, the journey becomes 80 years, an entire lifetime. And when you come back, everything has changed. Everyone you knew is older or gone. The world you left no longer exists in the form you remember. You did not just travel through space, you traveled through time. Now extend the distance, because most stars are not 4 light years away. They are dozens, hundreds, thousands. At 10% of light speed, a journey to a star 100 light years away takes 1,000 years, 1,000. Not a mission, not an expedition, a time scale longer than entire civilizations have existed. A journey that begins in one era and ends in another that no one alive at the beginning will ever see. And this is where the problem shifts, because now it is no longer about physics alone. It is about continuity, about whether a mission can survive long enough to complete itself. Because individuals cannot. No human can live 1,000 years. No crew can remain intact across that span. So the only way to make such a journey possible is to change the nature of the mission itself. This is where the idea of the generation ship emerges. A vessel not designed to transport a crew, but to sustain a population, a self-contained world, where people are born, live, and die without ever seeing the destination. A ship where the journey itself becomes life, and the destination becomes an abstract concept, a story, a belief, something passed down through generations, like a myth. At first, it seems like a solution. If no one can survive the journey, then send a civilization. Let it continue itself across time. Let it carry the mission forward. But this introduces a new set of problems. Problems that are not mechanical, not physical, but human. Because human societies do not remain stable across centuries. They change, they fracture, they evolve, they forget. Imagine life aboard such a ship, hundreds of years into the journey. The original crew is long gone. Their children are gone, their grandchildren, their great-grandchildren, all gone. The people alive now have never seen Earth. They have never seen an open sky. They have never stood on a planet. Their entire reality is the interior of the ship. Metal walls, artificial lighting, recycled air. To them, this is not a vehicle. It is the world. And the mission? The mission was decided by people who lived hundreds of years ago, people they have never met, people whose language, whose values, whose reasons may no longer make sense. Why continue? Why sacrifice resources, comfort, stability for a destination that no one alive will ever reach? Some will believe, some will not. Some will begin to question, others will begin to resist. Over time, those disagreements become divisions. Those divisions become conflict. Because history shows us something consistent. No society remains unchanged. Not for centuries, not for millennia. Even on Earth, with open space, abundant resources, and the ability to leave, societies fracture. They collapse. They reinvent themselves. Now imagine that process, compressed inside a closed system. No escape, no expansion, no external input, only the same population, recycling the same resources, over and over again. Every conflict has nowhere to go. Every mistake accumulates. Every failure is permanent. Now extend that further, 1,000 years, 2,000, 5,000. The ship is no longer a mission. It is an isolated civilization, one that has drifted so far from its origin that the idea of Earth may feel fictional, a story told in education modules, a legend, something that may or may not have ever existed. And the destination? A distant star, still thousands of years away. What happens when a generation decides that the journey should end, that the mission is no longer worth it, that life inside the ship is all that matters? There is no external authority to correct them, no communication with the origin world, no way to verify the purpose. The mission becomes optional, and over time, optional becomes irrelevant, because time erodes everything. Not just machines, not just bodies, but meaning, purpose, identity. Now consider the physical systems. A generation ship must function continuously, for thousands of years. Life support, water recycling, food production, atmospheric regulation, radiation shielding, navigation. Every system must operate, without failure, for time spans longer than any machine has ever survived. On Earth, even our most durable structures require constant maintenance, constant repair, constant replacement. Nothing lasts forever. Everything degrades, materials fatigue, systems fail, entropy always wins. Now, remove Earth. Remove supply chains. Remove external support. Everything must be produced, repaired, and replaced, using only what exists on the ship. Every failure consumes resources. Every repair reduces reserves. Every replacement brings you closer to a point where something critical can no longer be fixed. And when that happens, there is no backup, no rescue, no second chance, because you are alone. Now consider knowledge. Every system on that ship must be understood, maintained, and passed down across generations. But knowledge is fragile. It can be lost, distorted, misinterpreted. If a critical expert dies without passing on what they know, that knowledge disappears forever. And with it, the ability to maintain the system it supports. Over centuries, small losses accumulate, small errors compound, until eventually, something essential is gone, and it cannot be recovered. Now add time delay, because even if communication is possible, it is slow, painfully slow. A message sent across 100 light years takes 100 years to arrive. A reply takes another 100. A single exchange takes 200 years. By the time a problem is reported, the people who experienced it are gone. By the time a solution arrives, the situation has changed, or become irrelevant, or catastrophic. At 1,000 light years, communication becomes meaningless. A message takes a millennium to arrive. A reply takes another 2,000 years for a conversation. There is no coordination, no support, no connection. The ship becomes completely autonomous, cut off, not just physically, but informationally. Now consider something even more subtle, obsolescence. A civilization launches a ship. It sends it toward a distant star. The journey will take 10,000 years, but the civilization does not stop evolving. It continues to advance, to innovate, to improve. A few hundred years later, it develops better propulsion, faster ships, more efficient systems. A second mission is launched. It travels faster. It arrives sooner. The first ship is overtaken, becomes obsolete, still traveling, still carrying its population toward a destination that has already been reached. This creates a paradox. If you launch now, your mission may be outdated before it arrives. If you wait, technology improves. But if you always wait, you never go. So the rational decision is to wait indefinitely. And so no one launches. Now combine everything: distance, energy, time. Each one is difficult. Together, they are overwhelming. Because time does not just measure the journey, it destroys it. It erodes the ship. It fractures the society. It disconnects the mission from its origin. It ensures that by the time the destination is reached, the reason for going may no longer exist. And this is the deepest problem of all. Not that interstellar travel is hard, but that it may be meaningless. Because a journey that outlasts the civilization that created it is no longer a journey. It is an artifact, a relic, a message sent into the future, with no guarantee that anyone will be there to receive it. Even if they exist, even if they have the technology, even if they have the energy, time may ensure that they never arrive, or that if they do, it no longer matters. And this is where the universe reveals something profound. It is not just large, it is not just difficult, it is structured in a way that separates everything that lives within it. Distance keeps civilizations apart, energy limits their reach, and time ensures that even their attempts fade before they can succeed. And yet, even now, there is still one argument left, one final idea that refuses to disappear: the belief that somewhere, some civilization, has already found a way around all of this. That they are more advanced, more powerful, more capable than we can imagine, and that they have already solved the problem. But that idea rests on a misunderstanding. Because the laws we are dealing with are not technological limits. They are not temporary. They are not negotiable. They are fundamental. And in the next part, we confront that final argument. The idea that advanced civilizations can break the rules of physics, and why even that hope may not survive the reality of the universe. At this point, there is always one final argument. It appears in conversations, in comment sections, in late-night discussions under the stars. It sounds reasonable. It sounds open-minded. It sounds like the kind of thinking that refuses to be limited by human imagination. It goes like this: you're thinking too small. You're projecting human limitations onto civilizations that could be millions of years more advanced than us. They would have technologies we can't even imagine. They would find a way. At first, this argument feels powerful because it appeals to something deeply human: hope. The idea that intelligence always finds a solution, that every barrier is temporary, that given enough time, enough knowledge, enough progress, any problem can be solved. But there is a problem with this reasoning, a fundamental one, because the barriers we are dealing with are not technological. They are not limitations of current engineering. They are not gaps in our knowledge. They are properties of the universe itself. And that distinction changes everything, because technology can improve, engineering can evolve, understanding can deepen. But the laws of physics do not change. They are not suggestions. They are not guidelines. They are the rules that every particle, every atom, every civilization must obey. No exceptions. Not for us, not for them, not for anything. Let's examine this more carefully, because the idea of advanced civilizations is often framed in terms of energy. More advanced means more power, more control, more capability. And in 1964, astronomer Nikolai Kardashev proposed a way to classify civilizations based on exactly that: energy usage. A Type 1 civilization controls the energy of its home planet. A Type 2 civilization controls the energy of its star. A Type 3 civilization controls the energy of its entire galaxy. Humanity is not even Type 1. We are somewhere around 0.7. We do not yet fully harness the energy available on Earth. So when people imagine alien civilizations, they often imagine Type 2 or Type 3 societies, civilizations that can build megastructures, harness stars, manipulate entire regions of space. And from that perspective, interstellar travel seems trivial. If you can control the energy of a star, why wouldn't you be able to travel between stars? But this reasoning contains a subtle mistake. It assumes that having more energy reduces the cost of the journey. It doesn't. It only makes it easier to pay. And those are not the same thing. The energy required to accelerate a given mass to a given velocity is fixed. It is determined by physics, not by technology, not by intelligence, not by how advanced a civilization becomes. You can generate that energy more efficiently. You can produce it more easily, but you cannot reduce the amount required. The minimum cost is built into the universe itself. It is like gravity. Lifting a 1 kilogram object 1 meter above the ground requires a specific amount of energy. You can use your hand, a machine, a pulley, a robot designed by the most advanced engineers imaginable. But the energy required does not change, because it is defined by the gravitational field of the planet, not by the method you use. Interstellar travel works the same way. The energy required to accelerate mass to relativistic speeds is fixed by the speed of light, and nothing can change that. So a Type 2 civilization, with access to the full energy output of a star, can afford to launch interstellar missions more easily than we can. But they do not get a discount. They still have to pay the full cost, and that cost remains enormous. Launching a single spacecraft may consume a significant fraction of their total energy output for a period of time. Launching many becomes a major undertaking, and every mission still faces the same constraints: travel time, radiation, navigation, system degradation, communication delay. More energy does not remove these problems. It only allows you to attempt them. Now consider a Type 3 civilization, one that harnesses the energy of an entire galaxy. Surely, at that scale, the problem disappears. Surely, with that level of power, interstellar travel becomes trivial. But again, this is a misunderstanding. Because even with access to unimaginable energy, each individual mission still obeys the same physics. Each ship still moves below the speed of light. Each journey still takes time. Each system still degrades. Each crew still ages. The civilization can launch more ships, but it cannot make those ships immune to reality. It cannot compress distance. It cannot eliminate time. It cannot bypass entropy. It can only operate within the same rules, on a larger scale. And this is where the idea begins to break down, because scaling up does not change the nature of the problem. It only increases the number of attempts. Now let's address the next layer of the argument, the idea that advanced civilizations might discover entirely new physics. Warp drives, wormholes, faster-than-light travel. Concepts that appear frequently in science fiction and are often treated as future technologies, waiting to be discovered. But these ideas are not just unbuilt, they are unsupported. Warp drives, for example, require something known as negative energy, a form of matter that has never been observed, never been produced, and may not even be physically possible. Early calculations suggested that creating a warp bubble would require more energy than exists in the observable universe. Later refinements reduced that requirement, but only to the mass energy equivalent of a planet, still far beyond anything any civilization could realistically produce. And even if it were possible, there are deeper problems. Causality, the structure of space-time, the potential for paradoxes. The universe does not appear to allow faster-than-light travel, because it would break the relationship between cause and effect. Wormholes face similar issues. They require exotic matter to remain open. Without it, they collapse instantly. And even if they could be stabilized, they introduce the possibility of time travel, which creates logical contradictions that most physicists believe cannot exist in a consistent universe. These are not engineering challenges, they are theoretical barriers. They suggest that the universe itself prevents these shortcuts from existing, not because we lack the technology, but because they violate the structure of reality. And this brings us back to the most important point. The speed of light is not just a speed limit, it is a fundamental property of space-time. It defines how space and time relate to each other. It is woven into every equation that describes the universe. You cannot break it. You cannot bypass it. You cannot engineer around it, because you are made of the same reality that defines it. To break the speed of light would be to break the structure of the universe itself. And that is not something technology can do. So when people say an advanced civilization would find a way, what they are really saying is an advanced civilization would change the laws of physics. But if those laws are truly fundamental, then no amount of advancement can alter them, because advancement happens within those laws, not outside them. And this leads to a conclusion that is both simple and deeply unsettling. There may be civilizations far more advanced than us, millions of years older, far more powerful, far more intelligent, but they are still bound by the same rules, the same speed limit, the same energy requirements, the same passage of time. They may see further, understand more, build greater structures, but when they look up at their sky, they face the same barrier we do: distance, energy, time. And those barriers do not weaken, no matter how advanced you become, because they are not obstacles placed in front of you. They are the environment you exist within, and you cannot escape your environment, not completely. Even a civilization that has mastered its star, that has built megastructures, that has achieved levels of technology we can barely imagine, is still isolated, still separated from every other civilization, by the same vast distances, still forced to pay the same energy cost, still subject to the same erosion of time. They may reach nearby stars, they may explore their local region, but the galaxy remains out of reach. And beyond the galaxy, everything becomes even more distant, even more disconnected. And this is where the argument finally collapses, because it is not about whether advanced civilizations exist. They might, they probably do. The universe is too large for us to assume otherwise. But existence is not the same as contact. Intelligence is not the same as connection. And technology is not the same as transcendence. Because no matter how advanced a civilization becomes, it is still part of the universe. And the universe has limits. Limits that do not care how intelligent you are, how old you are, how powerful you are. Limits that apply equally to everything that exists within it. Even if they exist, they are still alone, just like us. And this brings us to the final realization, the one that changes how we interpret the silence of the cosmos. Because if civilizations are common, if intelligence arises again and again across the galaxy, then the universe may not be empty. It may be full, full of life, full of minds, full of beings asking the same question, but separated, permanently, by the very structure of reality itself. And that silence is not the absence of life. It is the absence of connection. Not because no one is there, but because no one can reach anyone else. The universe does not prevent life from existing. It prevents life from meeting. And once you understand that, the night sky begins to feel very different. Not empty, not lonely, but distant, infinitely distant, filled with possibilities that will never touch. We have looked at distance. We have looked at energy. We have looked at time. Individually, each one is overwhelming. But the true barrier is not any one of them alone. It is the way they combine. Because these are not separate problems. They are connected, interlocked. Each one amplifies the others. Each one makes the next more difficult. And together, they form a system that has no easy solution, no weak point, no obvious way around. Start with distance. The space between stars is vast. Trillions of miles, light years of empty void. To cross that distance, you need speed. Without speed, the journey takes too long. Thousands, tens of thousands, millions of years. So you increase velocity. But increasing velocity demands energy. And not just more energy, exponentially more. To cut the travel time in half, you don't double the energy. You multiply it, again and again, until the numbers stop being practical, until they become absurd. So now you face a choice. Accept slow travel and endure journeys that outlast civilizations, or pursue high speeds and pay an energy cost that borders on impossible. There is no third option, no hidden compromise, because distance and energy are linked. You cannot change one without affecting the other. Now add time, because even if you solve distance and accept the energy cost, you still have to survive the journey. And survival is not guaranteed. The longer the journey, the more things can go wrong. Systems degrade, materials weaken, biology breaks down, societies fracture, entropy accumulates. Time is not just a duration, it is a force that erodes everything it touches. So reducing time becomes essential. You want shorter journeys, faster travel, But that pushes you back into the energy problem, which pushes you back into the mass problem, which pushes you back into the distance problem. It is a loop, a closed loop. Every solution feeds into another constraint. Every attempt to solve one problem makes the others worse. And this is what makes interstellar travel fundamentally different from every other challenge humanity has ever faced. Crossing an ocean did not require breaking physics. Reaching the moon did not require overcoming a universal limit. Those were engineering problems, difficult, complex, but solvable, because the constraints were local. They were tied to Earth, to gravity, to materials. Interstellar travel is not like that. It is not constrained by a planet. It is constrained by the structure of the universe itself. And that changes everything, because you cannot engineer your way out of reality. You can optimize, you can improve, you can push closer to the limits, but you cannot remove them. Now consider what this means for any civilization, not just us, anywhere in the universe. They face the same equations, the same constants, the same limits. If they want to travel between stars, they must accelerate mass. That requires energy. If they want to reduce travel time, they must increase speed. That requires even more energy. If they want to survive the journey, they must maintain systems across time. That requires stability, redundancy, resources, all of which increase mass, which increases energy requirements, which feeds back into the system again. There is no escape from this loop, because it is not a flaw in our technology, it is a consequence of physics. Now consider the journey itself. A spacecraft leaves its home system. It accelerates, reaches high velocity, and then it enters the void, interstellar space, a region that is almost completely empty, but not entirely, because even in that emptiness, there are particles, atoms, dust, tiny fragments of matter spread across the galaxy. At low speeds, they are harmless. At high speeds, they become dangerous. At relativistic speeds, they become catastrophic. A single grain of dust, smaller than a grain of sand, striking a spacecraft at a significant fraction of the speed of light, releases energy comparable to an explosive. Not because the grain is large, but because velocity amplifies energy. Mass times velocity squared. That relationship does not care how small the object is. At high enough speeds, everything becomes a projectile. Now multiply that. Not one particle, but millions, billions, trillions, over years, decades, centuries. The front of the spacecraft is constantly bombarded, not violently at first, but continuously, relentlessly. Each impact tiny, but cumulative, eroding material, damaging systems, weakening structure. Over time, this becomes another form of entropy, a slow disassembly, one that no shield can perfectly prevent, because shielding adds mass, and mass increases energy requirements, which brings you back to the loop again. Now consider radiation, cosmic rays, high-energy particles moving at near light speed. They pass through matter, through metal, through shielding, through living tissue, damaging DNA, disrupting electronics. Over short periods, the damage is manageable. Over long periods, it accumulates. For a journey lasting decades, it is dangerous. For a journey lasting centuries, it is severe. For a journey lasting millennia, it is catastrophic. No material can fully block it. No system can fully prevent it. You can reduce the risk, but you cannot eliminate it. Now consider navigation. Over interstellar distances, precision is everything. A tiny error at launch becomes enormous over time. A deviation so small it would be undetectable on Earth can result in missing a target star system by billions of miles. There are no landmarks, no reference points, no roads, only distant stars that shift slowly over time. Correcting course requires energy, which increases mass, which increases energy requirements. The loop tightens, again and again. Now consider communication. Once the ship leaves, it is alone. Messages travel at light speed. The ship moves at a fraction of that speed. Communication becomes delayed, then impractical, then irrelevant. Eventually, the ship becomes completely disconnected, cut off from its origin. Its mission must continue, without guidance, without support, without correction. Every decision must be made locally. Every mistake must be absorbed. There is no safety net. Now combine all of this. Distance demands speed. Speed demands energy. Energy increases mass. Mass increases energy requirements. Time erodes systems. Time erodes societies. Radiation damages both. Dust impacts degrade structure. Navigation requires precision. Precision requires energy. Communication fails. Isolation increases. Everything feeds into everything else. This is not a single problem. It is a system of problems, a web. And every thread reinforces every other thread. There is no weakest link, because every link is strong, and they are all connected. Now imagine a civilization confronting this reality. They run the calculations, they simulate the journey, they estimate the cost, they model the risks, and they reach a conclusion. Not that interstellar travel is impossible, but that it is impractical, not worth the cost, not worth the risk, not worth the time. Because even if they succeed, the reward may not justify the effort. They may reach another star system, after centuries, after millennia, and find nothing, or something they could have found closer, or something that no longer matters, because their civilization has changed, evolved, or disappeared. And this is the final shift in perspective. The question is not, can a civilization travel between stars? In principle, yes. Given enough energy, enough time, enough persistence, it may be possible. The real question is, would any civilization choose to do it? Because the cost is enormous, the risk is extreme, the reward is uncertain, and the timeline extends beyond the lifespan of everything that gives the mission meaning. Rational civilizations optimize. They invest where returns are meaningful. They explore where exploration is feasible. They expand where expansion is sustainable. Interstellar travel may satisfy curiosity, but it does not satisfy practicality. It is not efficient. It is not scalable. It is not necessary for survival. And so, most civilizations, if they exist, may simply choose not to do it, not because they cannot, but because it is not worth it. And this leads to a conclusion that feels almost paradoxical. The universe may be full of intelligent life, but each civilization remains confined to its own region, exploring locally, developing internally, looking outward, but never reaching far enough to meet others. Not because they are incapable, but because the universe makes it irrational. And this is what transforms the problem from a technical challenge into something deeper, something structural. Because the universe is not just large, it is arranged in a way that discourages connection. That makes isolation the default state. That makes contact unlikely, not because of ignorance, but because of cost, distance, energy, time. Together, they do not just create difficulty, they create separation, and that separation may be permanent. There is no obvious way around it, no shortcut, no hidden pathway, no future technology waiting to unlock the stars. Only the same constraints applied everywhere, to everyone, for all time. Even if they exist, they remain where they are. Just like us, looking up, wondering, but never crossing the distance between them. After everything we have explored, distance, energy, time, a picture begins to emerge. Not one of emptiness, but one of separation. Because the conclusion is not that life does not exist elsewhere in the universe. In fact, the opposite may be true. The Milky Way alone contains hundreds of billions of stars. Many of them have planets. Some of those planets exist in regions where liquid water can form, where chemistry can become biology, and where biology might eventually become intelligence. If even a tiny fraction of those worlds develop life, and an even smaller fraction develop intelligent civilizations, then the galaxy could be filled with them. Thousands, millions, perhaps more. Each one evolving, each one building, each one looking up at their own sky and asking the same question we are asking now. Are we alone? And yet, when we look out into the universe, we hear nothing. No signals, no visitors, no evidence of contact, just silence. A silence so vast that it has become one of the greatest mysteries in science. Why is the universe so quiet? Why don't we see signs of other civilizations? Why hasn't anyone come here? This question is often called the Fermi Paradox, the apparent contradiction between the high probability of extraterrestrial life and the complete lack of evidence for it. But what if there is no paradox? What if the silence is not surprising? What if it is exactly what we should expect, once we understand the scale of the universe and the laws that govern it? Because the universe does not need to be empty to be silent. It only needs to be large enough that distance alone prevents contact, energy alone prevents travel, time alone prevents continuity. And when those three are combined, they create something that looks like emptiness, even if it is not. Imagine the galaxy, not as a crowded city, but as an archipelago, a vast ocean filled with islands, each island a star system, each one potentially hosting life, but separated from every other island by oceans so wide that no ship can cross them. Not because ships cannot exist, but because the journey is too long, too costly, too uncertain. So each island remains isolated, developing on its own, living out its own story, unaware of the others, or aware, but unable to reach them. Now imagine standing on one of those islands, looking out across the ocean, seeing nothing, hearing nothing. It would be easy to conclude that you are alone, but you are not. You are surrounded by other islands, other worlds, other civilizations. They are simply too far away for you to ever encounter them. This is what the universe may actually be, not empty, but disconnected. Not silent because nothing is there, but silent because everything is too far apart. And this changes the meaning of the night sky. Because when you look up, you are not looking at a map of destinations. You are looking at a map of separation. Every star you see is a place, a real place, with its own history, its own planets, its own possibilities. Some of them may host life. Some of them may host intelligence. Some of them may have civilizations that are looking back at us from their own distant world. But the space between us is too vast. The energy required is too great. The time required is too long. And so we remain here, and they remain there, separated, not by choice, but by the structure of reality itself. This realization can feel uncomfortable because it suggests something profound, that even in a universe filled with life, we may never meet it, that intelligence does not guarantee connection, that curiosity does not guarantee discovery, that existence does not guarantee interaction. But there is another way to see it, because isolation is not the same as insignificance. The fact that civilizations may never meet does not make them meaningless. It makes them rare, precious, each one a unique story, unfolding in its own corner of the cosmos, each one experiencing the universe in its own way, each one asking the same questions without ever hearing the answers from others. And perhaps that is not a flaw in the universe. Perhaps it is a feature, because if every civilization could easily reach every other, if the galaxy were fully connected, fully explored, fully known, then something would be lost: mystery, wonder, the sense of looking up at the unknown and feeling both small and part of something vast. Instead, the universe gives each civilization its own sky, its own horizon, its own journey, a journey that may never intersect with another, but is no less meaningful because of it. Because meaning does not require connection, it requires experience. And every civilization, no matter how isolated, experiences the universe in its own way. Still, there is something undeniably haunting about this picture. The idea that right now, at this exact moment, somewhere out there, another civilization may be looking up at their sky, just as we are. They may be wondering if anyone else exists. They may be imagining what other worlds might be like. They may be asking the same questions, hoping for the same answers, and they will never know that we are here. Not because they are too primitive, not because they are too far behind, but because the universe itself has placed us out of reach. We are hidden from them, and they are hidden from us, separated by light years of space and the unbreakable limits of physics. Two minds in the same galaxy, unable to touch, unable to speak, unable to even know that the other exists. And this is the silence we observe, not the silence of emptiness, but the silence of distance, the silence of energy, the silence of time, a silence that emerges naturally from the way the universe is built, not hostile, not intentional, just indifferent. The universe does not prevent life from arising. It allows it, encourages it, given enough time, enough chemistry, enough opportunity. But it does not make connection easy. It does not provide bridges between worlds. It does not shorten the distances. It does not reduce the cost. It simply exists, vast, expanding, unconcerned with whether its inhabitants ever meet. And so we are left with a strange truth. We may not be alone, but we may always be isolated, surrounded by life, yet unable to reach it, part of a cosmic community that can never truly communicate, a universe filled with voices that can never hear each other. And when you look up at the night sky, this is what you are really seeing. Not just stars, not just light, but distance, time, separation. Each point of light, a reminder that the universe is far larger than anything we were ever meant to understand. And yet, we are here, aware of it, able to see it, able to ask these questions. And that alone is extraordinary. Because even if we are isolated, even if no one ever reaches us, even if we never reach anyone else, we are still part of this universe. We are still witnesses to its vastness, still capable of understanding at least a small part of its truth. And maybe that is enough. Because the universe does not owe us connection. It does not owe us answers. It does not owe us companionship. But it gives us something else: perspective. The ability to look out into the darkness and realize just how vast it is, just how complex, just how indifferent, and still to find meaning within it, to build, to explore, to wonder. Even if the answers never come, even if the silence never breaks, even if the stars remain forever out of reach. Because in the end, the barrier is not intelligence, it is not technology, it is not will. The barrier is distance itself, and that distance is written into the fabric of the universe, unchanging, unavoidable, and absolute.